Let's see. Is this up and running and working? Okay, let's see if this works. Okay, so the primary, actually, to start with, the beginning of how this whole thing got together, I'm going to be talking about my efforts currently to design a compiler for the Co-Dfns language. We'll talk a little bit more about what Co-Dfns is in short order. But this came about largely because the CTO of Dialog, Morton, actually contacted me and said, why aren't you using Dialog? And I said, well, because of this, this, and this. And we started getting into a little talk, and eventually I started using Dialog, and he said, well, why don't you do something? And I said, okay, what do we do? And eventually that led to, well, let's write a compiler and do some interesting stuff with it. And so the first question here is, APL is already fast. For an interpreted language, it's actually very fast. And so it bears visiting just shortly why on earth we would actually need a compiler to begin with, or why we would even want one. And while Dialog does a lot of really interesting things in terms of idiom recognition, so we can take patterns of code in Dialog, and the interpreter will recognize those special cases and produce specialized code to optimize those cases. But that's not a very scalable solution when it comes to performance. If you take those idioms, you have to have a specific thing for each one of those idioms. And furthermore, there's really no checking. There's no real static analysis for APL in the interpreter. And so you don't get a lot of the potential benefits of error checking that you normally get in a compiler. Yes, while APL is fast, it's not fast enough for my purposes. And we'll see that in my benchmarks. I actually discovered a number of problems that the interpreter just can't handle in a reasonable way. And also, we get some static analysis. So I think, it's sort of a nice conclusion, but for a long time, APL hasn't had a compiler and they've gotten by on it. So what I mean to say is basically compilers do have something still to offer for the APL community, in particular in terms of performance, obviously, but also in terms of reliability. So let's start with where the current state of the compiler or the interpreter exists. So there's some inherent limitations to the Dialog compiler right now. One of them is that if you get into one of these cases, you can blow your cache constantly on a regular basis inside of the compiler. And on modern architectures, that completely destroys your performance and moves you from maybe a factor of 2 to, compared to C code, to a factor of like 100 or something like this. And that behavior is something that's very difficult for the interpreter to fix, because you just, the analysis that you need to do to fix that isn't easily done in an interpreter. And other sorts of analysis, like procedure calls and common optimizations that we get from compilers, just aren't available for interpretation. Things like copy propagation or constant folding, or even things like making procedure calls fast is not an option for the interpreter. And we don't get any nice static warnings about potential errors in our code, such as simple things like trying to add a number to a character. If we have a compiler, So Co-Dfns is sort of a headlong leap into a complete industrial strength compiler. It's not really an experiment so much as it is assuming we can write a compiler and do a really good job at it, and then taking that as far as we can possibly go with it. So this would actually never really have been on the table if we were talking about real APL. The APL of old, the APL that everybody loves and hates, that they grew up in, or maybe they saw in their high school programming or applied math classes, that APL really doesn't compile very well. And there have been a number of research compilers on APL before that looked at this and said, well, no. And the problem is that there are some features in traditional APL that makes it very difficult to compile enough that the benefits of compilation makes it worth it. You can do it, but you're not going to get the performance that makes it worth it to compile. However, John Scholes added a nice feature to Dialog APL called Dfns, which essentially restricts the language just enough to eliminate all of the nasty things that we don't like about APL from a compiler's perspective, and leaves all the goodies that we do like. So if we have Dfns, that provides a reasonable starting point for a compiler to actually get off the ground. Whereas if we didn't have this, and so let's look at some cases that we actually are concerned about with the compiler. In particular, this is one of the big things that the compiler has to offer is memory management benefits. And this is an example of one of the places where you can have horrible performance. And this is in large scalar computations. And Dialog already does automatic vectorization. So a single scalar primitive will be very, very fast, often faster than the naive C code if you don't have the right optimizations turned on in the compiler where it does all that pattern recognition. However, this is a line taken from an actual benchmark in APL, and you can find the Black-Scholes code for this on some of the classic APL papers. But this benchmark doesn't run very well because we have a number of things here that really mess us up. One is we have these multiple uses of variables here, and those variables are large vectors. And those large vectors get traversed once for each one of these calls. And they get traversed all the way through. And then you'll notice that all the rest of the operations here are just scalar operations. So really, there's absolutely no reason to traverse the vector multiple times throughout the course of our computation. And if we do the traversal, even if we're using vectorized operations, we're blowing our cache every single time, and possibly multiple times within a single iteration of this vector, and then refilling the cache with these same old arguments again and again and again. And this is one of the primary reasons in the interpreter for massive slowdowns in certain benchmarks for large scientific type of computations. And this is something that the interpreter is going to have a real hard time with. But a common optimization that we can see at this level is scalar fusion, which languages like Accelerate in Haskell, which is an array programming ESL for Haskell, that actually does this sort of operation and can take advantage of the cache to do these operations faster. Now, that was an example type of application, but the overall design of Co-Dfns is not what I call super compilation. Rather than aiming to create really super fast code without any input from the user, Co-Dfns is intended to allow very predictable and safe and controllable optimization with the aid of a tuning expert. So rather than going for this massive, super smart compiler that can interpret all your APL code and then make things go, instead we're aiming for giving the user the ability to do certain optimizations that otherwise wouldn't have been possible without the compiler. And the compiler itself will do a reasonable job of things, but it's not going to try to create unpredictable performance. And that's one of the things that I really am aiming for in the Dfns compiler is trying to eliminate variability in terms of performance when you're using the compiler. You should be able to predict or at least reason about the compiler performance without needing to run umpteen number of tests. So Co-Dfns isn't just Dfns. There is one aspect of the language which really is sort of at the heart of the intentions of the compiler, and that's there are two primitives, which are the complete extension to the Dfns language that makes up Co-Dfns. And this is essentially the single assignment empty vector. So it's a constant that is the same as a regular empty vector, except its fill argument, instead of being 0, is an empty single assignment cell. And then this is an operator, which takes a function and produces the same exact function, except that it runs that function asynchronously and returns a single assignment array, which will be filled with the results of that computation. And when Morton and I were talking, one of the things I really wanted to focus on was parallel performance, as opposed to what a lot of people focus on, which is sort of the optimizing the array expressions. And I care about optimizing the array expressions, but what I really am interested in is making it possible to reason about parallel APL code and make it in a sort of controlled manner. If we go back to this, if I change this to the empty vector, and I change this and just got rid of this, this function would be the exact same as the regular serial. This would be a valid way to write the serial version of this. And it would work the exact same way. And that's sort of an important property that I want to preserve in the language, is that we can reason about the parallel programs almost as easily as we can reason about the serial programs, provided that a few syntactic conditions are met to ensure determinism. In particular, if we write to any vector inside of a computation and spawn asynchronously on that, those writes have to be to single assignment arrays. They can't be to regular arrays. And if you do that, then you're going to have a deterministic program. It might deadlock on you, but it's going to deadlock deterministically. And furthermore, generalizing that a little bit, why is it so difficult in so many languages to actually reason about performance? We're timing. Okay, right. Okay. And so in a lot of languages, it's really, really difficult, especially high-level languages. It's very difficult to tell how fast your computation is going to go. Even in the dialogue interpreter, which is pretty straightforward, one computation which computes the exact same thing as the other and really looks about the same, unless you know the tricks, there's no way to predict which one's going to go faster. There's not a good mental model for the performance of the system, either in terms of memory or in terms of execution speed. And languages like ZPL, for instance, make a really big point of trying to make sure that you have certain properties that you can reason about that are highly correlated with the performance of your system, and especially parallel performance. So in the case of the language ZPL, which is partly inspired by APL, the two properties they care about is communication, when communication is going to happen from multiple nodes, and how many parallel nodes you're going to end up spawning. And so it allows you to get really good control over the type of communication that's going to happen whenever you do a parallel computation. So you know, in a distributed computing context, when you're going to get, for example, when you're going to have to broadcast to everybody, or when you can send data strictly to a single node and what that node is going to be. And this allows you to actually get some really interesting guarantees about the performance of your system. And we want Co-Dfns to, as much as possible, have that same behavior. And how do we reason about this behavior? Well, we already have APL, and APL is sort of like a math that you can use. And so why not use APL to reason about APL? And this isn't as crazy an idea as it might first appear. Lenora Mullen wrote her dissertation on the mathematics of arrays, which gave a way of basically axiomatically talking about APL using essentially APL as its description. And this is possible in part because so many of the properties that we care about in APL are actually described as first-class citizens in the language. So for example, the shape property, the domains, all of these things, those are all accessible in the language themselves. And so we can talk about them using APL and reason about properties of our programs using the language that we already know. So plans and schemes for this compiler, by the end of the year, we should have a usable version that people can actually start working with. And our intention is to target multi-core GPU and distributed systems, but with a real emphasis on integrating completely in with the dialogue system right now. This isn't going to be a new system. It's going to be a component attached to the dialogue system. And the effort is particularly on scalable parallel performance, as opposed to, say, getting the best vectorized code that we can possibly get out of our primitives. And to do that, we're really trying to make it possible for the compiler or the tuning expert to sort of have a dialogue back and forth between the code. So the compiler is not just going to do everything at once, and then the tuning expert just makes sure it gives the right code in. Instead, we want the tuning experts to be able to extend the compiler with optimizations that they care about, provided that they can demonstrate those optimizations are correct and safe in some level. And then to allow us to attach properties or contexts to those optimizations, and then allow the compiler to use those optimizations that we've given in the appropriate contexts whenever we want to, and have a reasonable assurance that we aren't breaking all of our mission-critical code in our pursuit of the ultimate. So while that's a nice scheme, version 1 is not going to have all of that. We're really aiming at the low-hanging fruit optimizations here, things like scalar fusion and good memory management at the lower levels. And then we will use that as a baseline for identifying and optimizing and developing the rest of the compiler from there, as soon as we have a little more feedback on the system. So to compare a little bit about the interpreter and the compiler and what the differences of the system are going to be, the interpreter is garbage collected. Whereas the Co-Dfns compiler, part of trying to make sure that we have predictable behavior, is being able to predict the kind of memory allocations and that we're going to get and how and when those are going to happen. So we're using a stack-based allocation scheme instead of garbage collection to do this. And instead of idiom-based special casing, which we probably will have at some point, we're focusing more on whole program style analysis or interesting general localized reasoning. And we want to try to make machine-checked proofs and verification of code correctness available to APL programmers at large, rather than leaving us in dynamic land with no hope of actually checking or talking about the code. So a common thing that we see in Usenet or in APL discussions is people writing out a long string of equivalencies between various APL programs to talk about how we optimize these things. But there's no machine checking to ensure that those are actually equivalent. And we'd like to make sure that you can write those equivalencies and then have some idea of whether or not they are equivalent using machine checking. And that feeds into the ability to create safe user-defined optimizations, where you as a tuning expert can develop your own set of tools for optimization and work on those tools so that when you get your client code in and need to optimize it yet again, this set of your bag of tricks is already encoded in a reasonable fashion, and you can just store that in your own Black Arts handwritten notebook somewhere. And the Co-Dfns compiler is going to be restricted just to Co-Dfns. We're not aiming to do the whole APL, and we're not aiming to really implement all of the dialogue system. We're just aiming specifically for the restricted language and then integrate it in with the rest of the dialogue system and leverage the numerous extensions that it supports. So in the end, once all of this is there, or even before that, the last thing that really drives the design of the compiler is that there should be less than trivial effort in order to use it for existing dialogue customers. So when you pull up your dialogue session, you just copy in a workspace and you just use the fix function there instead of your traditional fix for fixing one of your namespaces in. And provided that it's written in Co-Dfns and not traditional APL, you're good. It's all exactly the same to you. You don't have to do anything else. It just does its thing. And there's no real really significant change in workflow just to get and use the compiler. That does not mean you're going to get fast code. So you'll be able to use the compiler and we'll give you reasonable results, but we're not a magic act, and we're not going to be able to provide super code just from you taking your existing code. You will have to still have use the tools in the compiler to get these optimizations and to leverage them and apply them. And that's a slightly more manual process in Co-Dfns than in a traditional high-level compiler. So that is one of the sort of caveats of the whole system. So some coding goodies to just talk a little bit about what we have in the Co-Dfns system is the compiler is inherently designed and explicitly designed to allow easy integration with other people's code. And for the first time ever that I'm aware of, it will provide a portable, sort of easily used, complete parser for the Co-Dfns language, and produce it in a format and with a portable AST that can be used by any language and by any system, so that you can actually parse your APL code in its entirety rather than using a limited subset or doing really ad hoc parsing techniques. And I thought that this was something that should have been out there already, but apparently not. Apparently parsers are not a big issue in APL's 50-some years of existence. So this I don't think this should be new, but it appears to be new. And an additional thing is that the Co-Dfns language includes a complete functional specification of the language, which up to now also seems to have been lacking in the system. So when I searched around to find out what the Co-Dfns language actually was, I discovered user documentation, system code, and a lot of old wise wizards that knew how the language worked, but there was no clear, exhaustive description of the behavior of any of these systems or of the language itself and the kinds of responses that we should get. So part of the work in this compiler was to actually figure out what Co-Dfns is in its entirety in exhaustive, gruesome, excruciating detail. And so that is now done and available. And additionally, the compiler is designed to easily support multiple runtimes, so that for any given compiler instance of the compiler or any instance of a compiled piece of code, it's trivial to swap in and out at different runtimes, so that you can experiment with different runtime implementations and sort of easily plug and play with the runtime you care about. And this actually makes it a lot nicer to integrate with other languages. So if you can write your APL code in Co-Dfns, then you'll be able to easily embed that, for example, into other programming language frameworks, or connect between existing code that might be available as a DLL or as object files or source code with your APL code in a way that's a little bit less restricted than the current FFI in Dialog. So some acknowledgments. Dialog has provided significant funding and support for the project over the past year. And a lot of the ideas in Co-Dfns were inspired by things like mathematics of arrays, Intel's concurrent collection system, and a lot of the work on deterministic parallel that goes on at IU. And unfortunately, C++ too inspired a number of interesting things. I hate to say it, but they did. And the design of the compiler in particular is very closely tied with Andy Keep's work on using NanoPass to design industrial strength compilers. So at this point, we would actually demo some of the compiler at whatever state it is. Although at the moment, I don't have that demo prepared. Deadlines are horrible things. So that would come into play around this time. And then I apologize again for the slides. Yes.
So how hard is it to convert an APL program to Co-Dfns? I mean, or into dfunds if you don't care about parallel.
Very easy to convert functional programs that don't rely on dynamic scope or lots of mutation of global variables into Co-Dfns. Quite easy there. Assuming that you use actual structured programming techniques instead of Go-Tos.
Okay. How many normal APL programs would satisfy those rules to be? Would you expect that most people would be able to?
I would expect a significant portion of user-facing interface type code not to be portable, but for computationally intensive or high-performance critical type of code to be fairly easily portable.
So is there a way to mark a particular region of the code and say this should be Co-Dfns?
Yeah, you basically you abstract that into a namespace.
You try to get your kernels to be in that format and don't care about the rest.
Right, right. You basically abstract that into a namespace and then just call the functions from the namespace.
I think you were talking about this. I wasn't sure. So it is possible to have interpreted code and then compile this in APL.
They interact seamlessly together. Yes. Yes. Exactly. Yeah. That is part of the support from Dialog. The Dialog people will have to alter their system in order to support this concept.
Back and forth or just that?
No, back and forth. Yeah, yeah. That's part of the explicit intent of the compiler. You had a question.
Yeah, so there's a slide in the middle without a timer, and I felt a little cheated.
See, I threw that in there just because I knew that somebody would be expecting tigers in every slide. Cheetah.
I guess it could be.
Yeah. I think you have.
Are you using any conceptual name tracking or just the ideas?
I'm just using the ideas. I really wanted to use the framework, but it didn't work out.
Really cool.
Yeah. Part of the reason is that Co-Dfns is written in Co-Dfns.
Oh yeah.
So when and the NanoPass framework, it's actually really nice. And if there weren't other compelling reasons not to inject scheme into the rest of the system, I probably would have done it. But it's to reduce the number of dependencies and make it easier to deploy and embed and a number of other things. And I'm really taking advantage of this approach from NanoPass. So I'm basically doing everything except using NanoPass that I can. I think.
You talked about how you're not going to get it's not like a super optimized right off the bat.
Right.
And so there'll be this dialogue and whatnot. And so, what will the guy doing the tuning, the performance tester, what will he actually do? Does he write something down? Like, does he add annotations to the program, or does he push buttons in the IDE, or what?
So, the reason I didn't mention exactly is because I'm still sort of, that's an open design research question, is exactly the best way to do this. One of the things that I've been playing with already is I have an Isabelle file that allows you to prove properties about the codes of APL expressions. And the idea was if you insert annotations into your code, the compiler will spit out an Isabelle file. And if you do the proofs there, and then I wanted to be able to read it back in. I'm a little suspicious now as to how well that will work. But
so sorry, I think you're describing it for a low level of
okay. So
what it is that you're doing. So
fundamentally, the process of the tuning expert is twofold. One, to take an example program that you care about optimizing in a certain class of programs, and identifying the salient properties that allow you to do certain optimizations. So things like commutativity, associativity.
so you're talking about rewriting.
I'm
local rewriting kinds of optimization.
Both local and as global as possible. So things like, and again, the details of exactly how I want to do this are a little open, but the idea would be that if you annotate the program with certain properties, then you are then under some proof obligation to show that those properties hold, and then the compiler can take advantage of those using optimizations either that are built in or that you have written and attached to the compiler as an optimization library. So the idea is that a tuning expert, after doing this once, for instance, for a class of programs, would build up his own set of optimizations that he likes to use, and then use those. And those could either be shipped or applied automatically to other pieces of code, or be available for use as their own entities. Did that answer the question?
So I have two questions relating to Eric's question. So for nanopaths, so how did you actually end up having something that looks like a compiler that uses the nanopath structure, and how did you actually do that?
Well, it conceptually feels like nanopaths, but there are passes within passes within passes. So there's a high level concept of passes, and right now I think I have maybe 20 or between 10 and 20 passes that are there, and then each of the passes, rather than being designed on this sort of recursive case-based tree recursion, are doing global passes over the AST to do as much as possible there. So for example, in the parser, one of the passes eliminates additional annotation elements that were used for pretty printing the code. And that's, rather than doing a case tree walk, that's just a single statement that's like an APL expression that blows away all the lines.
But I think the nanopath itself, you don't take it recurring, right?
Right, you write these cases, but the cases are at like the individual element level, where, well, I guess I can, should I show you the code?
Maybe that's one moment for me to say, please show more complete things.
Yeah, the second part of my question is going to be, is it open source, and if not, can it be?